In this movie, you'll meet the normal distribution for the first time by looking at a typical normal distribution problem. So, looking at this information here, I've got two key things that are being explained to me. It says a machine fills a bag of chips with a mean weight of 250 grams. My mean is really important, so I'm going to underline this. And it's a weight. Weights are continuous measure. You can have half of a gram or a third of a gram. So any continuous measure can be modelled with a normal distribution. The other thing that we're told is that there is a standard deviation. Now, a standard deviation we haven't met before, but it's kind of like the spread. When we were looking before at inferences, we were always looking at the median of the two distributions, and to determine whether the median was any good to describe everybody, we looked at the spread, and we found that if you had a really small spread, the median was a really good descriptor of a typical person. When you're working with means, instead of using an interquartile range for your spread, you use something called the standard deviation. And later in this course, we will learn how to calculate that. But right now, you just need to know that that's the spread of the results. So I know that I have a mean and a standard deviation, and I know that I'm using a continuous measure. And that tells me that my result should be a beautiful bell curve. So what I'm going to do, I'm going to pause this for a second, and I'm just going to draw you a beautiful bell curve. So there we have our bell curve, and you can see that 250 is right in the center. That's the mean, median, and the mode. And you can see that I've put three little lines on the scale. Now, the common convention is that within 3 standard deviations, pretty much all of the results should have been captured. Now, you can see that my curve doesn't quite reach the axis. That's because we can't guarantee for sure that 100% will be in that range, but it's almost certain that things will be captured within 3 standard deviations. And if the value is not within 3 standard deviations of the mean, it's considered to be an abnormal value. So I'm going to go ahead and stop this video, and I'm going to put my standard deviations onto the scale. So my standard deviation is 5, so I'm going to be going up in 5s, and I'll see you in a minute. So I filled on my scale, and I looked at the question here. It said, what's the probability that a bag weighs less than 246 grams. So on the scale here, there's 245. I've put a little mark where I think around 246 is and drawn a section to chop off the curve. And I've shaded in the area. Now, interestingly, it's the area under the curve that actually tells us the probability. Because we're saying that almost 100% should be included within 3 standard deviations of the mean, then the area under the whole curve is 100%, or is 1. Now, if I can find the area under this part of the curve, then that will tell me the probability that a bag weighs less than 246 grams. The cool thing about about the normal curve is that the mean, median, and mode are all 250, which tells us that this half here and this half here are totally symmetrical, which means that if my whole area is 100%, then each half is worth 50%. Now, finding the area under the curve is not as simple as you might think. We could use calculus, but that would mean knowing the formula for every single normal curve that we need to deal with. And because the mean can take any value, it's just too complicated. And so someone came up with the idea of standardizing. They decided to record the areas under the curves where the mean was 0 and the standard deviation is 1. So this here, when the mean is 0 and the standard deviation is 1, this is called a standard normal curve. And there's a conversion that helps you turn any value in your curve that doesn't have a mean of 0 and a standard deviation of 1 into a standard normal value. So our conversion, we call the standard normal values or Z values. And to convert any value from the original curve, we could take that value, so for example the 246 would be the x, because that's the value we're looking to find. this little symbol here is a mu, and it stands for the mean. So in this question up here, that would be 250. And that little symbol is a little baby sigma. It's a not a capital sigma. And that is the symbol for standard deviation. So in this case, the standard deviation is 5. And so what happens is, it's the same conversion for every single curve, no matter what the mean is. We always take the mean away from the value and divide by the standard deviation, and that gives us our standard normal value, our z value. The cool thing about this z value is someone came up with a whole list of tables that show you the areas for a particular given z value. So here you can see the standard normal distribution, and this is the table that you will get in your exam. You can see that the numbers are really small, which is why I'm doing this video rather than showing you on the board. It's too hard to show you by hand. And so you can see that here's the standard normal curve up the top. There's the mean of 0, and that's the given z value. The bit that is shaded, or the area that is described in this table, is actually the area between the mean and the given z value. Because obviously the curve is symmetrical, it's also true that the negative z would correspond to the positive z. The area between the negative would be exactly the same as the area between the positive side. So I'm just going to move this for a second. I went ahead and did the conversion. So 246 was our x value, the number that we're looking to find. I took away the mean, 250, and I divided it by the standard deviation, and I got negative 0.8. So what I'm going to do now is show you the tables real close up. And I'm going to look down here for a z value of negative 0.8. Well, you see they're all positive, so I'm going to have to then look for a positive value of 0.8. So here we go, there's 0.8. Now I'm not looking for anything more than 0.8, 0.80, so this would be my number, my area. If I was looking for 0.811, then I would look across 0.8, 1, and then across here is a table of differences. So 0.8, 1, and then there's a 3 in the first column of differences. So I would add 0.0003 onto this. But since I'm only looking for 0.8, it's really nice and simple. It's just this number here, 0.2881. So interestingly, that's not me finished. You can see on the curve, so this is my standard normal curve, there is negative 0.8. The area that I've found, or the percentage that I've just found, is actually the red area. Now earlier, we talked about this whole thing being equal to 0.5 or 50%. So to find my actual probability that I do want, I would need to take this away from 0.5. So that's the question finished. And I've expressed my notation like this. The probability that x, the randomly selected bag, is less than 246 is 0.5 minus the area between the mean and the z value, which gives me a probability of 0.2119. The convention is that you give everything to 4 significant figures. That's great because if you're looking at the normal tables, everything's to 4 significant figures. So that's nice and easy, that's finished. Looking at the second question, the probability that the bag weighs more than this, well, I'm just going to put some more red on the diagram. So that's now the probability that the red area is the probability that the bag weighs more than 246 grams. Remember that the area under the curve is 1, so I can just work that out by taking this probability away from 1. So that's the probability that the randomly selected bag weighs more than 246 grams. And then if I was looking for the probability of between 246 and 256, I need to do a little bit more work. So I'm going to draw myself another sketch for that, and I'll see you in a minute. So I've gone ahead and drawn a standard normal curve, and I've put the z value of negative 0.8 on there, and I've shaded in between the mean and that value. So that z value is where the bags of chips were 246 grams. And then I've gone ahead and converted when the bags weigh 256 into our second Z value. So I did 256 minus the mean divided by the standard deviation to get 1.2. And I've shaded, or I've put a line up at around 1.2, and I've shaded in the red part to show the area there. Now I'd found this area before from up here. And so this number here, I'm just going to show you where I've got that from. I'm going to bring my standard normal tables back in. And this time I'm looking for a Z value of 1.2. So there we are, 1.2, and it's 1.20. So that's 0.3849. I'll just put it so it zooms a bit better. And so I've recorded that on here. And so my total area between the two Z values is actually 0.2881 plus 0.3849, and that will give me the probability that the bags weigh between 246 and 256.